At this point, we'll now discuss how to actually physically implement the control algorithms we've been designing. The first feedback systems were implemented mechanically, and so there are examples of this that we still see today, like the common toilet, how there's a float that automatically shuts the valve that fills the bowl when the height of the fluid has reached a certain level. Old thermostats with a bimetallic element in them implemented control mechanically, and the flyball governor was the means for controlling the first steam engine, a Watt steam engine. Today, algorithms are more commonly implemented in electronics and software. And so electronics are in essence an analog implementation, so they're continuous inputs and continuous outputs, just like we've sort of been assuming in all of the design that we've done so far. Examples include a passive circuit implementation and an active circuit implementation. So a passive circuit has only passive elements in it, resistors, capacitors. It has no external power source. And here's an example of an RC circuit. This example is a implementation of a lead compensator. And so lead and lag compensators and filters are examples of controllers or elements that can be implemented as a passive circuit. Active versions of these circuits also exist. So low pass filters can be an active or passive version. Lead and lag compensators can be active or passive. And so active circuits tend to include an amplifier, an op-amp, such as this example, and they require an external power source. And there are advantages and disadvantages of a passive or active implementation of a compensator or filter. We won't get into all the details, but one nice thing about active filters is they're not loaded down. And so this was something that we talked about when we discussed putting circuit elements in series with one another. The dynamics of one circuit can be affected by the loading effects of another circuit. Furthermore, these active circuits can also implement integration and differentiation, which passive circuits cannot. So in order to implement a PID controller as a circuit, you have to use an operational amplifier, you have to use an active circuit. This notion of the active circuits not loading one another down, you can also simply use the op-amp to provide isolation between even passive circuits. Aside from a circuit implementation, we can also implement our control algorithms in software. A software implementation tends to be much more adaptable. So if we wanted to change a control gain, we would simply go into our computer program, delete a number, and put in a new number. And we can also very easily implement sort of nonlinear logic or sort of binary logic. If these conditions use these control gains, if another set of conditions use these control gains. Something like that sort of switching logic is much harder to implement as a circuit. So more and more the industry is moving to implementation of control algorithms in software. An exception might be if you had a mass-produced sort of low cost margin product with a very simple control algorithm or control algorithm that's known to be fixed, such that you're just going to mass produce this thing and you really need to keep the cost down. It might be to your advantage to implement the controller as a circuit. But in many other instances, for example in the automotive industry and the aerospace industry, it's often much preferred to implement your algorithm as a program in software. In order to implement the control algorithm in software, it tends to be run on a digital computer. And so when you implement something digitally, you need to sample the input, you need to hold the output, and the equations must be discretized in order to implement them. And I'll try and explain better what all of this means, but it's different than what we've been doing so far. Everything that we've done so far assumes basically continuous dynamics. We haven't considered the sampling or the digitization of these algorithms. Another advantage of implementing something in software, aside from its adaptability, aside from the ease with which you can implement very complicated logic, is that it can also be generated automatically. So typically a lot of control system development is done in Simulink or some other sort of program, a high-level software environment that's suited to controls development and simulation, and even hardware-in-the-loop testing. And so the development engineer has this sort of high-level model of the control system, and he can generate the code that's going to run on board the vehicle just by hitting a couple of keystrokes, and it will automatically translate that Simulink model into control code that runs in real time on the vehicle. And we saw this a little bit in our lab exercise, but it's more and more the way that things are done. It's very fast to implement. It's very fast to generate. You sort of avoid transcription errors and things like that introduced by a human programmer. And while the code that's generated isn't always the most efficient, it's getting better and better. So here's a picture that's sort of representing a digital implementation of a control algorithm. So, you know, we have the sort of the continuous world. Here's our plant, but the controller is implemented on a computer, for example, in this dash box. And so the input to the controller must be sampled. You know, this program that's running that represents our control algorithm, it runs periodically and it takes some time. It's scheduled and it needs to run in concert with other algorithms. So you can sort of imagine, you know, we have this continuous output and this continuous command, and periodically the computer will sample that reference, it'll sample that sensor, and then it'll use that data point in its algorithm when it computes the control output. And so there's some frequency with which this sampling occurs and the program runs. It'll run once every 10 milliseconds or whatever. Similarly, the computer program generates an output periodically. And so on the input side, going from the analog world, the continuous world, to the digital world, we do sampling. We just take a sample of this continuous signal. On the output side, the way that we do the digital to analog conversion, the simplest way is to simply hold the output. So after the program runs and it calculates the next command, we just hold that value until it's able to run again and compute a new command. And so you can sort of imagine this staircase kind of shape where it calculates a new command, it holds it for that sample period, then it calculates a new command, holds it for that sample period, and so on. There are some implications of this sampling, of this analog to digital conversion and this digital to analog conversion. So one is we're in essence adding delay into the system. So we only sample a sensor every so often, every 10 milliseconds, and we only calculate a new control command every 10 milliseconds. And so by the end of that sample period, the sensor reading that we've used and the control command that we've generated is old. So we've basically introduced delay into our system. Whatever the sensor reading we had was, by the end of the sample period, it's now 10 milliseconds old. And similarly, whatever we commanded, by the end of the sample period, it's no longer sort of the most up-to-date. Another thing is that when we do this analog to digital conversion, we add quantization. You could imagine something like the number pi. The number pi is an irrational number. To represent it exactly, you would need an infinite number of decimal places. And obviously, no digital computer can do that, could store all of those decimal places. So at some point you have to round off. And so this depends on sort of the precision, or the number of bits in your processor, but at some point you're going to have to round off all of your values that you're inputting and also that you're calculating. So this round off error, if you have a very simple computer that doesn't have a lot of bits, it can be substantial. And when we do this sampling, we also need to be a little bit careful about the introduction of aliasing. So you could imagine that if we're sampling a periodic signal of a high frequency, for example, we have something that's vibrating, a drive line that's oscillating or something, a suspension that's oscillating. If we don't sample fast enough and we try and reconstruct sort of the underlying signal, we can get the impression that the underlying signal has a different frequency than it actually does. So a high frequency signal can get aliased down to a lower frequency. And so this is something that we need to be careful about, especially when we're dealing with very fast dynamics, very high frequency dynamics. Furthermore, when we implement our control algorithm digitally, we need to sort of discretize the equations. So everything that we've done so far, continuous differential equations, the Laplace transform with the Laplace variable s, all sort of assume continuous dynamics. To implement it on a digital computer, we need to use different mathematics. So for example, our differential equation models we need to convert to a difference equation, or we need to implement a difference equation instead of a differential equation. And so one way to sort of capture this, or to do this sort of conversion, is we can think of a derivative as a finite difference. So x dot is dx dt. It's the rate of change of x with respect to time. And in general, this is the sort of rate of change at an instant. But we can approximate it as a finite difference. We can approximate it as the amount of change over a period of time. And then we can sort of write this as a difference equation. This delta t is our sample period, and this index k corresponds to the number of samples. So if we have a sample at time t, that's our current sample, and then if we have a sample some delta t into the future, another sample period into the future, then we can consider that the next index, k plus 1. And so this is what we call a difference equation, and it's sort of a discrete version of x dot. Furthermore, instead of using a Laplace transform, we use something called a z transform. So a lot of the design that we've done use transfer functions that were a function of a Laplace variable s. We can similarly implement a discrete time version of a transfer function using the z transform. And so looking at our original differential equation, when we took x dot to the Laplace domain, differentiation in the time domain became multiplication by s in the Laplace domain. With the z transform, the z variable is sort of like a forward operator. So x of z represents our function at the current time period, and z can be thought of as an operator that takes us one step into the future. So if this is x of z, then x of k plus 1 is then z times x of z. Similarly, z to the minus 1 can be thought of as a delay operator. And so the question is, how do we design these digital controllers? One approach is to design it in the continuous domain, so do exactly everything like we've been doing so far in this course. Use the Laplace transform, use the root locus, use the Bode plot of the continuous dynamics. And then we can convert it into a difference equation, into a discrete time version. And so this approach here, where we used basically sort of an Euler's approximation, is sort of simple. It's not the best way. It's just to get the point across. There are much better ways than this to do this conversion to sort of guarantee that certain properties are preserved when you go from the continuous domain to the discrete time domain. The other option is to design directly in the discrete time domain, and all of that is sort of beyond the scope of this course, but if you take a specific course in digital control theory, you will learn about these techniques for conversion and for designing directly in the digital domain. So this brings us to the conclusion of Module 26, and basically we were discussing implementation of control systems, and we discussed again how to deal with some of the complexities of the real world, capturing all of the higher order dynamics, dynamics of the sensor, dynamics of the actuator, dealing with model error, dealing with unwanted inputs, disturbances, and noise. We discussed how to design a controller without a model, or at least without a model that's suited to controller design. So we learned some sort of heuristic techniques, either based on our intuition of the three terms of a PID controller, or using something like Ziegler-Nichols, these sort of heuristic rules for picking gains. And then we also discussed performing a sort of a numerical optimization, where we search over the entire space of possible control gains and pick the combination that minimizes some cost function or performance index. And we also discussed how to implement algorithms, either as a circuit in an analog way and in software as a digital control system. So this brings us to the conclusion of this course, and probably everybody's burnt out right now and they don't want to think about ever taking another control system course ever again, but I thought that I would list this anyways. Here are some other controls related courses that are offered at UDM that you may be interested in. And of course, this class, if you're taking it for the graduate certificate in advanced electric vehicles, a lot of those courses that you're taking can be transferred into a larger degree program, a master's degree in electrical engineering, a master's degree in mechanical engineering, etc. And so you may want to consider some of these other classes. The level of the course that you took is really sort of at the level of Controls 1. So having taken this course, you would be prepared to move on to Controls 2. And if you have any further questions or would like to discuss future courses that may be of interest to you, I'd be happy to speak to you about it.